In this video, we will learn about generative models and the variational autoencoder. So let's dive right in. Now we will focus on how one can generate new data with autoencoders. The idea now entails to randomly sample from the latent space. To remind you, the latent space is a bottleneck of an autoencoder network which we have previously shown in red and denoted as H in the previous chapters. A random sample means that we select random variables for all dimensions of our latent space and then apply the decoder part of the autoencoder to obtain a human understandable output. However, when applying vanilla or sparse autoencoders, which we have just seen before, now the generated data might look very unrealistic. Vanilla or sparse autoencoders try to achieve maximum separation between classes in the latent space to ease the reconstruction task. Consequently, we obtain very unrealistic results when sampling from the empty space. As a result, variational autoencoders were introduced which produce a continuous latent space from which sampling for data generation is now possible. In the next slides, we will focus on one application of variational autoencoders and then derive how a continuous latent space can be achieved. First, let's focus on a possible latent variable. In our example of artificial face generation, latent factors are, for example, gender, eye color, hair color, pose, and etc. As a human, we only observe a pixel, but we assume that the factors of variations of faces can be quantified. However, as we cannot directly retrieve these factors from the pixels of images, these factors are now latent. So the idea behind these latent variable generative models is that they explicitly model these factors using latent variables z. So if the latent variable z reflects these causal factors that determine the appearance of pixels in X, then the probability of this latent variable c given X should be an easier form of trying to model all the possible variations than in P of X directly. So this is what is shown here. So here we are interested in modeling P of X, but we're going to assume that the data itself is generated by some underlying factors, by some causal factors if you like, and these are actually underlying in these data. So you're basically breaking down this modeling problem into first choosing a context for the generation of the actual data. So you break it down into first choosing a latent variable z, and then from your condition, your generating process on that context z that you choose, and we are interested in then finding the joint distribution of the two, or then marginalizing out all of the hidden variables so that we have the actual data distribution. So if you think about this, this is used, for instance, if we have some data distribution that we want to model, and we want to model it with a mixture of Gaussians. So we want to use several Gaussian distributions that we mix together in order to model our data well. Or if you think about topic models, for example, this is another machine learning technique where this comes up. Topic models try to learn something about a large data collection, such as a collection of documents, for example, or large volumes of text. So topic models extract from it latent variables that you can associate with topics that underlie the documents that you see. So in this kind of modeling, you first assume that someone picked the topic, let's say sports or art, for example, and then all the words in the document that you're looking at are generated conditioned on that you choose sports or art as the topic of your document. Now the nice thing is then once we have a good approximation of P of X, we can then generate new samples, and if we train the model well, these samples will actually look very similar to the samples that we have in our training data. So they will be slightly different, but they will come from a distribution that is very close, and that's what we're after here. So you can use this for different purposes. For instance, in an artistic context, let's say given one style of art, we want to generate another style, or to, for example, generate new assets for a game. So given some cars, we want to generate similar looking cars, but a bit different cars. So you can use these then for creating video games, for example. Alright, so what we're going to talk about now is a variational autoencoder approach to modeling of these latent variables, or this generative modeling. So one important idea in this variational autoencoder approach is that we will use deterministic paths within a graphical model. So we still want to model the dependency or the relationship between these latent factors z and our visible variable x. But we will use a deterministic path g as part of this whole graphical model. So the nice thing is, if we, for instance, use a deep convolutional neural network as this deterministic path within this graphical model, this now allows us to create a very non-linear expressive mapping between these factors of variations. So between these latent variable z and the data that we actually have in our training set. So the idea is that the latent variable should be something simple, such as topics, for instance. So it should be some simple variables such as politics, sports, or art, and then from that you map to a collection of documents that all contain these, or in the case one for specific document that contains words that come from each of these topics. Then you can create a very complex mapping if you include these powerful neural networks as a part of the model. So one thing that we usually care about if we use these latent variable models is that we want our latent factors, or these latent variables, to really tell us something about the data. So if you think about these topic models that we just discussed, you know that the way that you use this is you have the training data and no one tells you the topic. So you can just dump a whole bunch of documents on this model, and in the end it will learn these factors z that you will then later on hopefully be able to interpret. So it's not like you're actually choosing the first topic and then you're generating the words. This is just modeling assumption. So in the end you want to learn these factors by itself. So you want to actually learn these topics that underlying the words of the document that you have in your training data, and as a result you will then have latent variables that are more humanly understandable. So in the first example, as we saw, the latent variables with faces are like either the pose of the faces, or the expression, or the gender, and so on. We don't have a guarantee for that, but there is a high likelihood, and usually we want our training to be set up in such a way that we can have a high chance of getting a nice disentangled factors of variation. Now the problem is, how do we actually get to z values that have anything to do with our data? So we could, of course, just put some probability distribution on z, and then we have to learn to generate new data. That's actually similar to what the generative adversarial networks do. We'll see that in the next video. But in this case, we will do this in an autoencoder framework. So where we will show a data point x, and then we want the model to infer the values of z that have some relation to our data. So there shouldn't just be some random noise in this case. So what we have to do here is basically we have to infer the values of these latent variables. We know x, of course that's the data that we see, And now we have to infer those variables that we cannot directly observe, which is the latent variables. So this is now the problem of inferring the posterior distribution of the latent variables given our visible data X. We know from the base formula that we can compute the posterior with this formula. So P of z given X is just P of X given z times P of z divided by P of X. So this is basically the posterior, and we get it by taking the likelihood of our data given our latent variables, and we multiply it with the prior over the latent variable. So that is z. So then we still need to divide by P of X. That's the data likelihood. Now the problem is that in order to get this P of X term, we have to basically marginalize out all our latent variables. So remember, we can get to P of X from the joint distribution of P of X and z by marginalizing out all the possible values of z. So the problem is that for many interesting models, especially models where we use deep neural networks as part of our graphical models, this will be very high dimensional, and there will be lots of interactions between a lot of variables, and usually this results in integrals that are intractable. So we want a model to learn latent variables that have some sensible relation to our visible data, and in order to do that, we need to train a model and we need to infer the posterior values, and that's P of z given X. One problem is that we cannot just simply compute it, because we cannot compute this integral here. So in order to be able to compute something that is reasonable, we will use the so-called approximate inference methods. Okay, so the idea in variational inference is that we want to approximate a posterior distribution, which is very complicated. So this is P of z given X. In the case of having deep neural networks as part of the graphical model, which models the relationship between z and x, we cannot directly compute it. So what we can do though is to choose some form of simpler distribution Q that has its parameters of its own, and then we optimize the parameters of this distribution Q so that it gets as close as possible to the actual posterior, which we cannot directly compute. So that's the main idea behind variational inference methods. So what we'll then do is that we'll choose some distribution Q of z given X, and we now want to make it as close as possible to the real posterior, which we cannot compute. So in essence, how do we measure the difference between the actual posterior and the new distribution Q that we just introduced? So that we can do by looking at the KL divergence. So the KL divergence between some distribution Q of z given X and the true posterior P of z given X is basically the expectation with respect to this distribution Q of log of this ratio here, which is the ratio of Q of z given X divided by P of z given X. Then this measures the mistake that we make by using the distribution Q rather than the distribution P. So we can rewrite this a little by using the fact that the log of this fraction is just the log of the numerator minus the log of the denominator. And then we did another step here where we basically rewrote this P of z given X as the joint distribution between P of z and X and divided by P of X. So that is just the definition of the conditional distribution here. Then we can again pull out this part from the
the fraction that you see here, and again use the fact that in this case this would be minus log of p of x, and then we pull this out because it doesn't depend on z here, and so we can just pull it out of these parentheses, and now this is a nice expression for the KL divergence. So we realize that we still have this log of p of x here, and again we cannot directly compute this because this would invoke integrating over all the hidden variables of z, which is intractable. So we still have a chance of making this whole thing smaller anyways by choosing an approximate q. So we rewrite this expression little bit now. So we now solve this whole thing for log p. So what we get here is that we can express the log likelihood of our data as this whole term here. So we have this minus this expectation with respect to the q distribution of the latent variables given x of log of q of z given x minus the log of the joint distribution of p of z and x. And then there is basically this term of the KL divergence that measures the difference between the q distribution and the p distribution of the posterior that you see here. So what we can observe in the KL divergence that has a minimum of 0. So this is the posterior. So what we can observe here is that at minimum the KL divergence is 0, and that's the case if q of z of x is exactly equal to p of z of x, and this whole term that's left will be equal to the log of p of x. So we cannot directly calculate the KL divergence, but this minus the expectation with respect to q of this log of q of z given x minus log of the joint distribution. So this is basically a lower bound on the log likelihood of the data. So this whole thing is the lower bound on the log of p of x, and it has its own name. So it's basically called the evidence lower bound, or sometimes also called as the variational lower bound. So this means that log of p of x is at least this plus the mistake that we make by using the q distribution rather than the p of z given x. So whenever we minimize the KL divergence, that we would make this lower bound tight. So rather than minimizing this KL divergence, what we can also do is to minimize the lower bound. So they're both functions of our distributions q, and when we maximize our distribution q, this will also lead to minimizing the KL divergence. So it is an indirect minimization of the KL divergence, if you like, and we maximize this lower bound, and thereby we minimize the KL divergence, and then we make this whole expression as close as possible to log of p of x. So this is basically what we will now use in variational autoencoder models. So the variational autoencoder has this special setup now in which it does this variational inference. So it uses two neural networks. It has an encoder network which has its own parameters phi, and all the weights that are there in these parameters is of the distribution phi. So our distribution q is now parameterized by this whole function here f that takes the input and the data x, which has its own parameters phi, and the so-called encoder, and this is the so-called encoder network. So we also learn a decoder network, which will now take a sample from the latent vector z, from the approximate posterior that we are learning with the encoder. And from that sample, then we will generate a new sample called x hat here. So we'll generate a new samples x from our latent variable that we sample z, and we have a neural network in the middle. So the network g of z, and this is again how we parameterize this in case of our reconstruction network or the decoder network. So we are going to then generate p of x given z with parameters theta here. So and this is just p of x given g of z. So these two blocks that will be connected in this variational autoencoder framework. And the nice thing, as we see, is that we can then actually backpropagate through this, and we can train this whole thing at one go using backpropagation, as opposed to the other methods which have to resort to much slower training and inference mechanisms. Okay, so what we saw how the parameterization looked like for the variational autoencoder using these two neural networks. And now we can write this elbow for this evidence lower bound that we had on depending of the course on x, but also depending on the parameters of these two networks. So the encoder networks that has parameters phi, and the decoder network that has parameters theta. Now we take the expectation with respect to q sub phi of z given x of log of p sub theta of z, comma x minus log of q sub phi of z given x. So that's almost the same as before, but now of course we have to make the parameters more explicit here. So we can again rewrite this a little bit by splitting up this joint distribution into p of x given z and p of z. And the logs will make the sum out of this product. So we have this log of p sub theta of x given z plus log of p sub theta given z. We can further summarize this against two different terms. So we can summarize the expectation of these two terms as the KL divergence between a prior over our latent variable z. So this is p sub theta of z, and it's just a prior on the latent variables and our approximate posterior, the q sub of phi of z given x. So if we use this lower bound, this elbow, as our objective in training the network, then this will basically act as a regularizer, trying to force the Q network to stay as close to the prior distribution over the latent variables. So wherever it tries to make this very different, it will incur a penalty. So we also have to do a good reconstruction. So we have to generate new samples of x given whatever samples of z we sampled from our posterior. So the learning in this model is sort of a trade-off between these two forces, and we want to have the accurate reconstruction of our input images or our input data in general, but we can only modify the latent distribution as much as needed. So the traditional autoencoder networks, the deterministic ones are sometimes a bit tricky to train, and they make them not overfit. But these networks, the VAEs, are self-regularizing, because this regularization term, according to the data that we use, you still have to choose the dimensionality of your latent representation, but then you have this inbuilt regularization in this network. So this makes it quite a bit easier to train than the regular autoencoder networks. Okay, so there's basically one more ingredient missing in order for us to be able to sample this Z from this approximate posterior distribution that we learn in the latent space. So the sampling operation is actually not a continuous operation, so it doesn't have a derivative. So how do you do backprop through that? So basically that's the key question here. So what comes to the rescue is something that's called as the reparameterization trick. All right, so now we use the example where we say our latent variable Z is distributed according to some Gaussian distribution with mean mu sub Z of x and variance sigma sub Z of x squared times now the identity matrix. So this is a diagonal covariance matrix. So then if we, I will explain this figure in the following slides. So then if we set up our random variable Z to have these two deterministic paths, mu sub Z of x plus sigma sub Z of x times some epsilon that we see here, then we sample from a normal distribution with zero mean and with the identity matrix as the covariance. Then it does not depend on P or Q. So what we have to optimize are these two deterministic paths. So there are outputs of our neural networks in the encoder, and we can do this in the decoder, but for now let's stick with the encoder alone because it's output Z. So this is the deterministic part, mu sub Z of x, and this is also deterministic, basically the sigma sub Z of x. So this randomness comes from this sort of auxiliary variable which doesn't have any relation to the parameters of our encoder or decoder. So we sample it and then we multiply the standard deviation in order to actually get the random variable. So since the moments, the mean and the sigma are parameterized by a neural network and these are actually deterministic, so this makes it possible to now do backprop even though we use the sampling operation. So we can also do this reparameterization for the x's, and if we then again want to create a random variable x down there, we can do that. Now I think this is much more easier to see with the visualization. Now in this visualization we can see that so originally if we were not to use this reparameterization trick, our flow looks something like this that we see here. So here we have the deterministic nodes that are basically shown in gray, and then the weights of the network as well as basically the input vector, and then we have this stochastic node Z which is shown in blue that we are trying to sample from. So as we saw, we cannot do backprop because we are going to get stuck at this stochastic sampling node, and so when the network's basically parameterized like this. So instead, when we reparameterize, we get this diagram that you see here. So we have now diverted the sampling operation off to the side here. So so we now have this sampling operation off to the side to this stochastic node epsilon, which is drawn from a normal distribution. So now the latent variable Z is deterministic with respect to epsilon, the sampling operation. This means that we can now backprop through Z without running into errors that arise from having the stochasticity. So this simple reparameterization is what we actually allows VAEs to be trained end to end. Okay, so now basically we have all the ingredients. So we have this reparameterization trick that allows us to put this whole thing together. And we get the inputs from some data points X, and we put this through the neural network, and we output the moments of the distribution that we use for Z. We sample the noise variable, and then we get our actual sample Z, which is then input to our decoder networks here, which gives us some value X hat that should resemble the input as much as possible. So then we can compute the difference between these samples and the original X's, and we can back propagate the error. So in the end, we still have the expectations in the KL divergence, but also we have these expectations with respect to the approximate posterior distribution Q. But in practice, we'll just approximate that through the Monte Carlo samples. All right, so if you look at the pseudocode, so this is the algorithm from one of the variational autoencoder papers. So basically, the variational autoencoder was sort of independently discovered by two research groups. So one is Kingma and Welling from University of Amsterdam, and another group was also from Google DeepMind. So both of them basically had the same idea, and they released the archive paper almost exact same time. But they published at slightly different conferences. But usually we attribute VAEs to both these papers. So basically here we just show you one of the algorithms. So here you see the algorithm for mini batch training of the variational autoencoder. So you just choose the initial parameters randomly, and then you sample the mini batches of m data points that you get from your full data set. So you sample your vector epsilon from your noise distribution, P of epsilon, and then you compute the gradients of this elbow that is dependent on the parameters theta and phi, and also of course on the data in your mini batch and whatever noise vector that you drew. So if you have Gaussians for both the approximate posterior distribution and also for the prior over the latent variables, then you can just calculate the KL divergence in the closed form. So we still need to sample variables. We still need to sample anyways in order to compute these expectations. So we do that with the mini batches. So we then take the gradient of this elbow with respect to both the parameters, and then just update this using the gradients that we get. So what they say in this paper, that they use mini batch size of something like 100, and in order to estimate the expectation for this term, they only used one sample. So they could in principle have sampled many Z's and generated many images, and from that they would estimate this expectation here. But they found that in actually just drawing one sample is what's giving them a good enough results. And this basically has an additional regularization effect. So you do that until convergence, and that's basically this whole thing that you see here, like how exactly you set up your distributions and so on. But in general, this algorithm is very simple. All right, so let me show you an example. So a very nice property of these variational autoencoders is that they basically learn these smooth latent spaces. So very nice example is this faces data set that you see here. So here we have one dimensions in our latent space, and here we have another dimension in our latent space. So this could be basically Z1, and this could be, for example, Z2. And the factor of the variation that the model extracted along the Z1 direction is something like, let's say, the rotation of the heads, if you can say that. So all of these heads are slightly rotated, and basically then the factor, let's say along the Z2 direction, it's something like facial expressions. So there's different expressions as we go along the Z2 directions. So these images are created by sampling from a uniform grid in the Z space. So you sample these points uniformly in the Z space, and then you put them through a generator. So you sample here, 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 and so on and so forth, and they just plotted this along these sampling points. So another example is this MNIST data set that you see on the left here. So you remember that these are basically these handwritten digits. So here it's not quite so obvious what it learns across these two dimensions. So here, yeah, it's not quite obvious. So this is from this example is basically from the deep learning book. So, but there is transitions between different numbers on these both axes, and there's a smooth interpolation between different numbers, and also the orientations as we see here. So as I said, there's no guarantee that you will get something that is as nicely as interpretable in these cases of the Frey faces data set, where you have these poses and expressions. But there are actually engines of this VAE which use more regularized terms to put more pressure on generating actually interpretable factors of variations or latent variables. And in general, they learn quite nice representations in the latent space. Alright, so this brings us to the end of this video. I have 3 repetition questions for you. So the first is, what is the idea behind generative models? The second is, what is the reparameterization trick? And the last question is, how do you train variational autoencoder? So you can pause this video at this point and we'll continue at the next one.